Good morning, everyone. I'm Nat Tuck, and this is cs4610 or cs5335, Robotic Science and Systems. It's cross-listed as both an undergrad and graduate course. There's a couple extra requirements on some assignments for graduate students, but otherwise it's one course with two different numbers. Because of the ongoing pandemic, we're going to be doing a flipped style class. So each week I'm going to post a set of video lectures like this one, and then we will have optional in-person class meetings at the normally scheduled lecture times where I'll do some demos in class and you can ask questions. For the first lecture, it'll be more lecture-y just to get everybody to the video lectures, but going forward, lectures, the in-person meetings will be secondary to these video lectures. An important thing about video lectures and doing them every week, especially for a class that I'm both designing and teaching this semester, is that the video lectures are not going to be perfect. I'm going to do them largely in one take. I'm definitely not going to do any complicated editing. So these aren't going to be the highest quality video lectures ever, but they should be sufficient to get the information that's necessary for the class across to you all students. In this class, we're going to be exploring control programs for mobile robots. That's one of the aspects of computer science, of robotics that's interesting in a computer science, from a computer science perspective. And so that's what we're going to be talking about. That raises some questions. First question is, what's a mobile robot? So in order to be a robot, I'm convinced that something has to have sensors, which allow it to sense the world, actuators, which allow it to do stuff and interact with the world. It has to have a computer in it that's running a control program, and that control program needs to access the sensors and use the actuators to demonstrate some sort of autonomous behavior. If you have someone remote controlling something and that defines all the behavior, that's not a robot, it's a drone. If you have something that doesn't have a computer in it, it's something other than a robot. If you have something without sensors or without actuators, it's something other than a robot. We need those four things: sensors, actuator, control program, autonomous behavior. For something to be a mobile robot, that just means that some of the actuators cause the robot to move, like they might spin the wheels. Now, in this semester, we're going to be talking about robots primarily in simulation. I was hoping to do more physical robots. Physical robots are fun, but because of the realities of the pandemic, there aren't going to be so much physical robots this semester. There will be an optional physical robot that you can get and work with for some assignments later in the semester. I'll get to that in a little bit. Now, in order to see more examples of mobile robots, I have 3 demo videos. Because I'm not doing editing, you're going to, after I talk about which video we want to discuss, you're going to pause this video, go ahead and watch the video I'm talking about, and then come back and resume this video. So the first video that I want you to go watch is the self-driving car video. You go do that and then come back. Alright, you saw the video. I apologize for the dramatic music and everything. That is a useful example of a mobile robot. That self-driving car has all of the properties that we need. It has sensors. It's got the camera in the cell phone, which allows it to see what's in front of the car. It has actuators. By hooking up to the computer in the car, it's able to control the smart cruise control that the car has, which allows it to control the speed within some limitations, and allows it to control the steering. It has a control program running on the cell phone, and it has autonomous behavior. The car will drive itself, following lanes and avoiding obstacles, while the control program is running. Unfortunately, we don't get to use a car as our robot for this semester. Cars are kind of expensive, and actually the OpenPilot software there has solved all of these sort of easily accessible, interesting problems that we could talk about with self-driving cars in this class. So that's not what we're going to do, but that's still a good example. Pretty much all cars are getting this sort of self-driving behavior, and that means that pretty much all cars are going to be robots in the future. All right, example 2. Go ahead and take a look at the video about the SpaceX launch. You watch that and come back. All right, you're back. So spacecraft are almost always robots, especially spacecraft that are unmanned, space probes. You can't really remotely pilot a spacecraft. There's 2 core problems. The first one is that when you're going through atmospheres, or when you're going behind things, like if you want to have a spacecraft go behind the moon, you can't get a signal in real time to the spacecraft at all. So if the spacecraft needs to do anything during those windows of no signal, it must have autonomous behavior, otherwise it can't have any behavior at all, because you can't remote control something if you can't get the remote control signal to it. The second problem that spacecraft have is that as you get further away from Earth, the distance becomes so great that you start having speed of light issues. Just to get a signal to the moon takes more than a second. Round trip, more than 2 seconds. So if you want to try to do a race car on the moon, remote control, like drone pilot that race car, you better have pretty wide turns, or your race car might fly off the road just because you have 2 seconds of lag in all your control inputs between seeing what's going on the screen and being able to have the race car on the moon respond to your commands. When we get to things that are further away than the moon, like Mars, we're talking about really long signal delays. The average delay to Mars is something like 10 minutes. That means a round trip time of 20 minutes. You're not going to do anything interactive remotely piloting something on Mars. The Mars rovers that they have, even though they try to plan out step by step exactly what they're going to do, they still have to have autonomous behavior. The Mars rovers must be robots just in order to make the thing work. If like a rock falls and the Mars rover needs to stop so that it doesn't run into the rock, it can't wait for a human to make that decision. It has to decide that right away, because otherwise it would have long run into the rock and caused whatever damage and broken stuff long before the human would even see the signal, much less the control signal could get back to control the robot. The SpaceX launch is a good example. The way they do that is they press one button that says launch. They have a bunch of people monitoring what's going on, and all those people are ready to intervene in different ways, but in general they just press a launch button and the SpaceX rocket launches itself, the booster disconnects, the booster lands, and it all happens autonomously. One really neat thing about space robots, unlike autonomous cars, is that they're a useful thing for us to actually deal with in this class. We have a good simulator that will let us simulate spacecraft and simulate autonomous control for spacecraft. And so we're going to be doing a bunch of assignments in Kerbal Space Program that take advantage of this. I'll have a demo mission where we have a spacecraft do something sort of inefficiently in Kerbal Space Program in today's lecture sequence. Finally, go ahead and watch the video about the teaching robot. And I'll wait for you to do that and come back. So that robot went ahead and did a maze, and that's sort of a typical assignment for a robotics class like this. Frequently the way it works is that the instructor will hand out these teaching robots, one teaching robot to each team. Each team will be assigned to write the control program that allows the robot to solve the maze, and then maybe at the end of the semester you'll race the robots to see who can solve the maze faster. In the video, we saw that the girl who was working with the robot had programmed it to solve the maze. She pressed one button, the robot went ahead and solved the maze entirely autonomously, and then it was done. It had accomplished its task. Didn't do it like the most efficiently possible, but it only has one IR sensor to see whether there's a wall in front of it, so there's a limitation on how complex its behavior can be. And that sort of maze following thing is something that we are likely to be able to do in simulation later. We're going to be using the gazebo simulator to simulate wheeled robots. And we may do a maze assignment in simulation, and then it would be really nice if we could do a maze assignment on a real robot. Now, I'm going to pause for a second, and I'll be back in a second. All right, I'm back. Here is the MBot Ranger robot. This is a robot kit that you can pick up for about 120 bucks. You can assemble it pretty easily. It took me, I don't know, I have a video of it, but I think it took me about half an hour to assemble this from the parts that came in the box. It's got a bunch of aluminum extruded pieces that you can assemble in a whole bunch of configurations. This is just the default configuration that they recommend in the starter kit. And this was my initial plan for what we were going to do this semester. Everybody was going to buy their own robot, build the robot kit, get this guy, and then we were going to, both with the gazebo simulator and then on the physical robot after we had things working in simulator, do assignments like maze solving. Now, this is still something that I would like you to buy, but it's optional. We're not going to be spending the whole semester on it, so this is a little bit expensive for me to require if I'm also requiring you to buy a Kerbal Space Program for the rocket simulations. But if you would like to work on a real robot, you can go ahead and get this guy, and this will be one of the options for your final project, is to write a control program that uses this robot to solve some task. This robot's pretty exciting as far as what it can do. It does only have the sonar sensor here for seeing things, but it has things like a accelerometer in it, so you can do neat balancing tricks. Go ahead and the next video I want you to watch is the balancing example with this robot. Go ahead and pause this video, watch that, and then come back. All right, so you saw it. It was in like a triangle configuration. It was like balancing like this. Yeah, this robot can do that. That would be a cool thing that might be a component of a final project for this class. All right, let me put this off to the side, then I'll be back with our next thing. So as I said, that particular robot kit is optional for this class, and none of the things where you'll potentially use it are going to happen in September or early October, so you can hold off even deciding if you want to deal with it until we're a little bit further into the semester and you have more information about what the assignments are going to be and which things are sort of interesting. But yeah, physical robots are an option. My plan B for this course, if we weren't going to use physical robots at all, was to just teach the entire semester with Kerbal Space Program as our simulator. That would be super cool. Autonomous control of spacecraft. But I figured people would be more excited by a combination of the two ideas, looking at traditional teaching style robots, and then having a significant portion of spacecraft. These are both robotics issues where we're doing autonomous control, and they look at things from a sort of very different perspectives. You have different problems in the two domains. Now, it's sort of relevant to what's going on in this class, who I am and why I'm teaching a robotics class. So I am not a robotics researcher. The normal reason that people teach classes like this one is because they are robotics researchers. They have a robotics lab, and the thing that they're trying to do is recruit grad students to help them do robotics experiments so they can write papers. Now, I absolutely support that scheme. Getting cheap labor by running classes is a wonderful plan. It's good for everybody involved. But I am not a researcher at all. I purely teach university classes here at Northeastern. And my goal is to try to get people to learn as much as possible. And in order to get people to learn as much as possible, people have to have fun doing stuff that's hard. And robotics is great for that, because robotics are a ton of fun, but robotics are definitely difficult. The thing that makes them difficult, at least the interesting thing that makes them difficult from my perspective, is that we have a bunch of systems integration problems. You end up with a bunch of different pieces of software, and you have to get them all to work together, and you have to understand all the different layers of the sort of abstraction stack that you're dealing with. So for example, if we want to run stuff in the gazebo simulator that is, I don't know, driving down a simulated road between lines, because we want to simulate an autonomous car, we have to know how to run a program on Linux, because Gazebo wants to run on Linux. We have to know how to do the inter-process communication that lets our control program talk to the Gazebo simulator. Gazebo uses Google protocol buffers as its message transport. We need to have some understanding of protocol buffers, or the whole protocol buffer thing gets horribly confused. We need to be able to understand how to simulate a camera. This is a physics problem. There's a whole bunch of things involved in either simulating or just using a camera in robotics that you have to have some idea what's going on with, because we need the camera to see the lines that we're going to follow. And then we need to be able to do the computer vision. We need to do all of this in the sort of time constraints that we have of then being able to have sort of artificial intelligence in the traditional sense make decisions about how the robot should act in response to what it's seeing through the camera. And there's just a whole ton of moving parts. A whole ton of moving parts is great. We get to play with it. That's what makes me think robotics is a ton of fun. I did a bunch of robotics in grad school. It was great. Now I teach primarily systems courses, and it turns out that all of that is sort of prerequisites for robotics, even though robotics people don't necessarily want to like believe that that's true. All right, so we've taken a look at the physical robot. We've talked about that stuff. All right, so I'm going to take a break from filming full screen, and we're going to go over to a computer, and we're going to take a look at the course website and see how is this course structured, and how is everything going to work out this semester.